Hey y'all, my name is Tragan Barbell, and today we're going to solve a problem. The problem we're going to solve particularly is going to be a 2D array maze, and the reason why I think this array maze is a good problem to solve is because we can visualize it and we can draw from like real life experiences. If you've ever tried to traverse a maze, whether it was um, in an application or at a restaurant when you're a kid and they gave you this placemat to try to get reach to the exit of the maze successfully. Uh, and two-dimensional arrays really represent these things really well, in the sense that we can have these nested arrays, which represent rows and columns inside of a larger array, and that's exactly what a 2D array is. So, for example, we have 1, 2, 3. This array in here, which is an element of its outer parent array. Then we have another array here, which is an element again. And then we have 1, 2, 3, which is the third element of this inner array. And if you're familiar with arrays, you know that you can access the elements by its index. For example, this would be index 0, 1, 2 of this outer array, because arrays in computer science are base 0. And then to get access to the inner array, not only do we have to access this outer array, but then we need to access the element here by keying into the array even further or iterating through the array one more time of an O of n squared way. So now we would have to say in computer science, if you're using I and j, we can say array at I and j, where j is the length of the inner array, where j is the element in the inner array, and I is the array itself. Great, so now we have a pretty good understanding of 2D arrays and how it may look like a maze. We can continue to the code. So here we are, back on a Replit. I've gone ahead and created this maze 2D array. I called it my maze, and the reason why it's a good reflection of what a maze is because each cell, so each element inside a nested array either contains a 0, 1, or 2, whereas 0 is an invalid space or a blocker, 1 represents the path, and the 2 represents the exit. Right now we only have a single 2 and it's a single exit, and our entrance point would be where we have a 1. So you can imagine this element right here at 2, 1 is a valid space, and anything around it that's a 0 is an invalid space. Anything that's a 1 around it, we can really count that as valid. So when we're here at 2, 1, we have to check top, bottom, left, right, not the diagonals at this point, but top, bottom, left, right, and see if there's any 1s. If there's a 1 or a 2, if there's a 1, we have to store, the current cell that we're at in a way that we can track it as visited, so we don't come into the issue of bouncing back and forth when this is a 1 and the one below it is a 1, and likewise the one above it is the one we just came from. But then we can continue traversing top, bottom, left, right until we reach a 2 or until we don't reach anything at all. So I've gone ahead and made some pseudocode-ish game plan. And we're going to create a function that takes in a maze, and we're also going to create a helper function that we're going to use recursively to create a stack. And by using the call stack, we have to do a couple things inside. We have to, well, before we use the call stack, we have to check to see if the cell is a 2. That way we could short circuit right away and exit successfully. If the cell is a 1, we have to reassign the value of that cell to, let's say, a visited string is a good way. So that prevents us from going back and forth from already visited. And then if it is still 1, we can make a recursive call to check top, bottom, left, right. And we can also think about how we could protect ourselves from going out of bounds. So we can go ahead and start coding right now. We're going to use a class for this one. So we're going to say, let's call it function maze solver. Takes in a maze. And because it's a class, we have context to this.maze equals maze. Great. And now we have to create that inner function. So we can say this.traverse is a good name. Is equal to a function that takes in a column and a row. Column and row will serve the purpose of I and j in that sense. So we have this function that takes a column and row. At this point, we can say that we can short circuit it. Say if this.maze at the column at the row triple equals 2. Can maybe just console out log. We have successfully exited the maze. But now we have to check to see if it's not a 2. We have to see if it's a 1. And checking if it's a 1 will eliminate all the other constraints where it's like a 0 or some other value that's not a 2 or a 1. So here we could have an else if this.maze at column and row is strictly equal to 1. We have to be able to do a couple things. We need to reassign the value. So this.maze at row at a column at row is equal to string visited, sure. But then we also have to make a recursive call to iterate through. So for this, we're going to have to talk about our edge cases where we go out of bounds. So if this.maze length, right? So if the column is less than this.maze length, you need to call the traverse method on the column and move up 1 and the row. And if the row is less than this.maze column length, you need to traverse the column and the row, move it up 1. And then if the column is greater than 0, we can traverse again, traverse the column minus 1 and get rid of the row. Then if the row is greater than 0, of course, traverse the column and the row minus 1 So this looks good. Let's try to create an instance of maze solver. So const ms equals a new maze solver and give it pass in my maze because it expects a maze. Now ms has access to traverse method, so we can call it ms.traverse, and we're going to plug in 2, 1, which is the coordinate of this one right here, and let's see what happens. So it said we successfully exited the maze, but I guess to better understand the path that we took, we can also maybe console.log the column and the row here. And you can see this is the path that we took. 2, 1, 3, 1, 4, 1, 4, 2, 4, 4, or 4, 3, 4, 4, 5, 4, 6, 4, 7, 4, 7, 5, 7, 6, 7, 7, 8, 7, 8, 8 until we reach 8, 9 right here, the exit. So that's been a maze solver. Thank you very much.